Going to solve the second problem of the fourth partial exam of electricity and magnetism that says like this. A long straight wire runs along the y-axis. The wire carries a current in the positive direction that is changing as a function of time according to I, that is the current, equal to 2 amperes plus 0.5 amperes over second times the time. A loop of wire is located in the xy plane near the y-axis, as shown in the figure that I'm going to draw in a second. The loop has dimensions 7 meters by 5 meters and is 1 meter away from the wire. What is the induced potential difference in the wire loop at time equal to 10 seconds? So here we have our wire. Here is the wire in the y direction, and here we have our current, and here we have our x axis, and here we have the loop of wire. Here we will have the magnetic field that is getting smaller because it's getting far away from the current. So this is equal to our magnetic field. And here we are said that we have 7 meters, and here we are said that we have 5 meters, and here we have 1 meter. So here we have 1 meter, and until here we have up to here we have 8 meters. Okay. And we have the current equal to 2 plus 0.3 times the time. Okay. Once we have this, we can determine the magnetic field with this formula, that the magnetic field is equal to mu naught times the current over 2 pi times the radius. And we also can use the Faraday's law. The Faraday's law said that the potential difference is equal to minus the differential on the change of the magnetic field divided by the differential of the time. And we also can use the Ampere's law, that is the one that we have been used until today, until now. We have been using until now. That is exactly this part is equal to Ampere's law, that says that the integral of the magnetic field times the differential of the area is equal to this part. Okay, once we determine this, we can work with this part to obtain the potential difference. Okay, then we are said that this is equal to this. So we said that the magnetic field times our area, but we know that the area is this part times this part. So we will say that it's the x-axis that we can express it as this times the y, and we know that the y is equal to 5 meters. So this will be equal to 5 meters. And so we can take it out because we're not going to work with that part because it's a constant. So this is equal to 5 times the integral of the magnetic field, but we are going to work now with the x-axis from 1 to 8. So we're going to integrate from 1 to 8. So is the integral from 1 to 8 of the magnetic field times the x. Okay, so here is the x, okay, but we know that the magnetic field is equal to this expression, as we said before. So if we substitute this part, we can say that 5 times the integral from 5 to 8 times mu naught times the current divided by 2 pi the radius dx, and but instead of the radius we can determine here an x, because we are working with the distance as terms of x because of the differential we have here. So once we are determining this part, we can solve the integral. I'm going to solve it up here. The integral, that is this expression, because we established in here by this formula, is equal to the integral of b. Oh well, no. I'm gonna go directly to the result. Is equal to 5 mu naught times the current, but the dx goes up like a logarithm. So this divided by 2 pi, because they are constant, times the logarithm of x evaluated from 1 to 8. And this is how you solve the integral. So then this is equal to 5 times mu naught times the current divided by 2 pi, and logarithm of x, well, instead of x I'm going to write 8, because it's this one, minus 1, logarithm of 1. And we know that logarithm of 1 is equal to 0, so we're only left with a logarithm of 8. So once we know this, we know this part of the expression of potential difference, that is this part. So we're only going to to find these two parts to solve our problem itself. So the expression will be equal to 5 mu naught the current divided by 2 pi times, well, I'm gonna to erase the current in here, and I'm going to express it in here because it depends on the time. So as I write it in here, I'm going to rewrite our expression of potential difference, that is this one minus d of v over dt is equal to all this part, 5 mu naught over 2 pi logarithm of 8, and this is exactly this part. Okay, now this will be multiplied by di over dt, and dt, we know that our time is given, the time we are given are 10 seconds, and the current itself is 2 amperes plus 2 amperes plus 3 times. Okay, so what we are going to take into consideration is what is multiplying by the time. Okay, so the expression of the relationship between the amperes and the time will be equal to 0.3 amperes over second. Okay, so once we substitute this value into here, we are left with this equal to mu naught. We know that it's 4 pi times 10 to the minus 7, so it's 5 times 4 pi times 10 to the minus 7, this over 2 pi, because it's from here, times the logarithm of 8 times 0.3. And once we have all our values, we only have to take a calculator and obtain our final value, and we will obtain 6.24 times 10 to the minus 7 volts. And that is the final result for the potential difference of this problem.